Okey, saya ni. Okey, Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. Sebelum kita mulakan majlis, kita baca umum kitab. Mudah-mudahan majlis akan lebih diberkati. Al-Fatihah. Alhamdulillah, bersyukur kita kehadirat Allah SWT. Pada petang ini kita dapat menjalankan sesi kolokium pada bulan Mei 2022, manakala kolokium pada bulan yang lepas terpaksa ditangguhkan kerana Hari Raya Aidilfitri. Jadi pembentang pada petang ini ialah Dr. Rinie Narinie binti Muhammad Nasir. Jadi latar belakang pendidikan beliau, beliau telah memperoleh Dr. Falsafah daripada Universiti Islam Antarabangsa dan master beliau daripada Universiti Putra Malaysia. Degree beliau juga di Universiti Islam Antarabangsa. Tajuk pembentangan beliau pada petang ini ialah Mutually Unbiased Unitary Basis and its Context in Uncertainty Relation for Unitary Operators. Untuk mengetahui dengan lebih lanjut berkenaan pembentangan beliau, tanpa membuang masa, saya mempersilakan Dr. Rinie Narinie untuk membuat pembentangan. Dipersilakan, Dr.
Okay, Assalamualaikum warahmatullahi wabarakatuh and very good day to you. Okay, first of all, thank you Dr. Alkos for the brief introduction. Okay, first let me share you my screen first. Okay, I'm going to present you my research work, which is mutually unbiased unitary basis, or we call it MUB, and its content in uncertainty relation for unitary operators. So for your information, this is under the area of quantum information theory, and I did this work actually with my main supervisor during my PhD year, which is Associate Prof. Dr. Jasmine Shamsul Shari from International Islamic University Malaysia, and also my course along with my course supervisor, which is Professor Stefano Mancini from University of Camerino, Italy. Okay, so we divide into few sections, which is the first section will be the construction of MUB, where we're going to define a more generalized definition of MUB, and then based on the equivalent relation between MUB and MUB, which is mutually unbiased basis for MES, which is maximum attended states. So based on that, we're going to find provide a straightforward numerical search for MUB for space of MDC. So moving on, we have next section, which is on mutually unbiased unitary basis in prime dimensional Hilbert space. So we're going to define mapping between the inner product spaces of D-dimensional Hilbert space, HD, and D-dimensional subspace of MDC. So if you take a look, this is two inner product vector spaces, okay? So, and then we're going to define a binary operation to form an algebraic structure called the monoids here. So, and then we try to resolve it into an isomorphism between the monoids of HT and monoids of the dimension subspace of MDC here. And then only then we can find the maximum number of MUB for the dimension subspace of MDC. So moving on, okay, we already defined the definition of MUB, which is more generalized. We find the maximum number of MUB for D-dimensional subspace of MDC. So in the next chapter, we're going to look at how is the precise role of MUB in the context of unitary operators. So that's all, okay. Okay, moving on. Okay, first, what we should know about. So actually, our work in mutually unbiased unitary basis or MUB is actually motivated by the mutually unbiased basis, MUB, which refers as alternate basis of a Hilbert space. Okay, when we talk about Hilbert space, it's actually a vector space and inner product vector space actually, such that the transition from any one state in one basis to any other state in another basis is equiparable. So if we have an unknown state cat U, Okay, where when we talk about CatU, this is a quantum mechanics notation. When we refer to a vector, we say a state. A Cat state here is prepared in one basis of d-dimensional Hilbert space. So let Cat states of Cat R and Cat S be the guesses, which is these two are resulting from a measurement. Okay, be the guesses for Cat U. Then the inner product between Cat U, Cat R, and Cat U, Cat S would have a common value. So in other words, a state prepared in one basis gives maximal uncertainty when measured in another. So for example, if we take a look of D is equal to 2, which is basically a two-dimensional quantum system, i.e. a qubit, a state from this basis, okay, which has two elements in it, is actually mutually unbiased with the standard basis, which is Cat 0 and Cat 1. So the notion that we want to realize that we would like to have an analogous idea of equable guesses to bases consisting only unitary operators for some subspace of MDC. So it means that when we do the trace of inner product here between that U, unitary U to the guesses UR or US would share a common value. But this is only bases consisting of unitary operators only. So in this section has been reported, the findings has been published into two journals, which is Physical Review A and a Special Issue International of IJQI. Okay, this is actually when I went to Italy for conference, international conference in 2019, just before COVID. Okay, so the notion of MUB for entire space of MDC was first actually reported in Scott 2008, saying that two sets of operator bases with each cardinality T0 and T1 are actually mutually unbiased if the Hilbert-Schmidt inner product between these two bases is equal to 1. So Scott also stated that a complete set of MUB for space of MDC can at most have D squared minus 1 and the same word provided for construction for D is equal to 2, 3, 5, 7, 11. So whereas our definition of MUB is more general compared to the equation 2 to include our MUB for some subspace of MDC, which is as follows. So this is our definition of MUB. We consider some n-dimensional subspace of vector space of MDC, two distinct orthogonal bases composing of unitary transformation. We say F0 and F1 are MUB provided the Hilbert-Schmidt inner product between those two bases is equal to some constant C. And then some constant C must not equal to 0. Why? Why is it so? Because if it's equal to 0, it means that these two elements are from the same basis, which is that is not the definition of our MUB here. Okay, if it's equal to 0, it means it's from the same basis. Whereas we want the element coming from two distinct bases, and then resulting in some constant number. Okay, moving on. Given the equivalent relation between unitary operators and maximum entangled states, maximum entangled state is any bipartite quantum system consisting of two subsystems where when you do the partial trade, you get 1 over D. Okay, and then the search of MUB is actually tantamount to the search of MUB consisting of MES. So when we are trying to look for MUB, our word MUB is actually equivalent to the search of MUB consisting of maximum entangled state here. So for a unitary, so if we have our unitary YI, is equivalent is actually cat YI is in HD tensor HD, which is can be written as is equation 4. So based on this, we will present a very simple approach in finding the minimum number of MUB consisting of MS for HD tensor HD with a number approaching maximum number, which is D squared minus 1, as the dimensionality D gets larger. So in Wishnia 2011 described that given a bipartite state, a complete set of MUB can be formed by either first product state and maximum entangled state, or second solely by partially entangled state. It means that one can only have a complete set of MUB if that complete set of MUB formed by either these two. Okay, so we refer the following lemma from Rinie on the complete set of MUB, saying that in a complete set of MUB that contains only D plus 1 product MUB, all other bases contains only MES. So we let DA and DB is equal to D, with D being prime number. Thus, we have the following corollary, saying that the minimum number of MUB consisting of MES is actually D multiplied with D minus 1. And then based on that, we find the ratio of the maximum number of MUB, which is D squared minus 1, to minimum number of MUB for MES, which is we just found just now. Okay, D multiplied with D minus 1. And then we plot the graph against the prime number D. So in this graph, we can see that actually this is first 24 prime numbers D. You can see that it approaches unity. But in this graph, it does not tell us whether the maximum number of MUB, which is D squared minus 1, can be achieved. It only tells us that as D gets larger, you can approach some number. Okay. However, in our paper here show that for D is equal to 2, the number of MUB for MES is actually 3. Therefore, we can conclude that for HD tensor HD with D prime number, one can always construct at least 3 MUB for MS. So this is equivalent to having 3 MUB for D squared dimensional space of MDC. Okay. So this is how we provide a straightforward numerical search for MUB. So we consider the D squared dimensional space of MDC with the canonical basis given by equation 7, where this X and Z actually the generalized Pauli operator. And then we define another basis in equation 8 here, where this unitary operator Y here is written as equation 9. And then the following two conditions must then be met, which is the first one is unitary condition, and the second one is the Scott definition of MUB for entire space of MDC. So and then we select this gamma RS to be some primitive root. And then we set the algorithm for the computer to search for all possible D squared minus 1 element of this set given the condition above. So if this Y is actually mutually unbiased to all elements in the standard basis, therefore equation 10 is true. Okay, so let us summarize the numerical step. So we have a canonical basis K, and then we define another basis L. So we set the algorithm for numerical search to ensure the basis K and L fulfill the two conditions C1 and C2. Only then we can say that K and L are mutually unbiased to one another. So however, the search to construct MUB does not confirm the uniqueness of the construction since there is no proof that no other construction resulting in different sets of MUB exist. So we have not yet proved the uniqueness of the construction. Okay, so it means that yes, there may be some possible way to construct MUB other than this kind of way. So moving on mutually unbiased unitary basis in prime dimensional space. So in this section, we actually want to have a constructive theorem for number of MUB for D-dimensional subspace of MDC. Just now we discussed about the full space of MDC. This section is particular for D-dimensional subspace of MDC. There's a difference. Okay, and then what we meant by constructive theorem here is that in a sense that we would like to have a recipe for the maximum number of MUB. So first we limit ourselves to the D-dimensional subspace of MDC, with D also being a prime number, and then the standard basis can be written as equation 11, with X to the power of 0 is actually the identity operator, and then we have the X to the power of I, and X to the power of j is actually xi or plus j. And then we know that the trace of inner product between these two is equal to 0. It means that X and Xi and Sj actually in the same basis, they are orthogonal to each other. So this kind of subspace we shall refer as MS for simplicity. So beginning with the computational basis, we have this kind of basis for standard basis. So the remaining D MUBs can thus be written as equation 12, where the index of R and S here indicating of the basis and the element of the basis respectively. So let us define a map G from HD, this D-dimensional Hilbert space, and the MS we just referred just now with the rule of, okay, we see that G acts on this arbitrary element where AI is the coefficient for every vector Ki, and we can see that AI is actually a complex number, the coefficient. And then G actually maps the Ki to the one in MS, Xi. Okay, so next we provide the relation between the inner product of D-dimensional Hilbert space and MS in the following lemma. So we have any two cat states, which is cat phi and cat psi, which is those are in the D-dimensional Hilbert space system. And then we have the G acting on the cat phi and G acting on the cat psi in MS. So the inner product on HD, which is this guy, is actually proportional to the inner product on MS, which is this guy. Okay, and then the proportional constant is actually 1 over D. So ensuring that MUB are mapped to bases for MS, which is mutually unbiased to one another, we give the following lemma, saying we have two bases, B0 and B1. Okay, these bases are in the D-dimensional Hilbert space. So we see that B0 and B1 are mutually unbiased to one another if and only if the sets of this and this are bases for MS, such as the Hilbert-Schmidt inner product between these two is equal to D. However, the mapping between the basis of HD and the basis of MS provide no clue whatsoever whether the basis consists of unitary operators or otherwise. Yeah, there will be mapping between basis of HD and basis of MS. So how do you make sure that the basis of HD is really mapped to the one basis of MS that only consists of unitary operators? So in order to determine that, we shall first need to define a mathematical structure by defining an algebraic structure, by defining a particular binary operation, and then form a monoid, and then resort to an isomorphism between monoids of HD and monoids of MS. And then this is the mapping would be looks like for the monoids of HD and monoids of MS. Okay. So let us find a binary operation here, which we call this bullet on the set HD. So for all cat psi and cat phi in D-dimensional Hilbert space given as equation 14, so we let this bullet be a function from HD times HD to HD be as in equation 15, where I O plus J modulo D is equal to M. Okay. So the monoid of HD is isomorphic. We have another lemma saying that the monoid of HD is isomorphic to MS, i.e. there is a bijection mapping from HD to MS such that for all cat psi and phi in HD, okay. So it shows that when we show that this is okay, this is as is, and then this is true lah. Okay, this is true. And then we define the conjugate transpose of a state. Okay, this is our definition of conjugate transpose. So we have a cat state here, okay, in the dimensional Hilbert space, and then we define our cat conjugate transpose of this cat state to be as this. Okay, D minus the cat state will be D minus I. Okay, then, okay, this lemma is very important because only this lemma shows that the mapping between the bases of HD, the monoid of HD will definitely map to monoid of MS, which only consists of unitary operators. So when you do a cat state bullet with its conjugate transpose, which is equal to cat 0 if and only if this is true. It means that when you have a unitary operator conjugate with its transpose, definitely it's going to have a unitary identity operator. So this lemma gives us a way to check if the G maps a state in HD to unitary operator in MS. So moving to the next lemma, saying that the maximum number of MUB for a D-dimensional subspace of MDC is actually strictly less than D plus 1. Actually, this lemma is very long. This is based on the equivalent relation between unitary operators and maximum rectangle state. However, we managed to prove it that the maximum number of MUB of consisting MES actually is lesser than D plus 1. So equivalently, the maximum number of MUB is actually lesser than D plus 1 for D-dimensional subspace of MDC. So now we come to a theorem saying that the maximum number of MUB for D-dimensional subspace of MS is actually D. So we define the conjugate transpose of this cake state, which is we have from the equation 12, if you just remember this. This, okay. And then we do the conjugate transpose of it, okay, as equation 17. Thus, to determine whether this cake state actually will be mapped to unitary operator, we consider the following. So we have the cake state from equation 12, bullet with its conjugate transpose that we get from equation 70, and then you have this is simplified version. This is more simplified version, and from equation 18 actually you have we have simplified again into equation 19, and from equation 19 actually you can gather the coefficient, which is this one, okay, the omega thingy here, okay, is given by equation 20, and then based on equation 20 you have two cases, which is the first one when R and S, where R and S, this R and S is actually equal to 0, we have the coefficient for every cat, regardless the value of M being 1. So this implies that when you do the conjugate transpose, you cannot get cat 0. So thus the element of cat state here where R and S is equal to 0 cannot be mapped to a unitary transformation under G. Hence, at least one MUB cannot be mapped to a unitary basis for MS. So we know that for MUB, the complete set of MUB is D plus 1. So when D plus 1, 1 cannot map, so only D left. So for what about case 2? So in the case of R is not equal to 0, but M is equal to 0, the coefficient becomes 1. Thus, for M is not equal to 0, there's a property of it. This is property in the, I think in the some books in quantum information thing. The property saying that the coefficient will be definitely become 0 for M is not equal to 0. Hence, we have that when you have cat state here, bullet with its conjugate transpose, where R is not equal to 0, you definitely get cat 0 here. Thus, we conclude that only D MUBs of HD are mapped to MUB for MS. So what does it say? It says that the maximum number of MUB for D dimensional subspace of MDCs is only D. And then we have a recipe for it based on the monoids just now. Okay, moving on for section 4. Okay, what we have done. Okay, recall what we have done in the preceding section. Okay, section 2, we generalize more definition of MUB, and then we find the minimum number of MUB can be achieved on D squared dimensional space of MDC, which is we can get at least 3 for D is equal to 2. So the maximum number of MUB is approached for very large values of D. Okay, this is true. And then section 3, the construction of maximum number of MUB of MS. Okay, we have a constructive theorem where in the sense that it gives us the recipe of finding maximum number. It just not give you just maximum number, but it gives you the recipe of the construction as well. However, after all we done in MUB thing, So it is not clear the precise role of MUB other than the role played in the quantum process tomography of Unitary channel by Scott 2008. So basically the definition of MUB captures the notion of indistinguishability between unity operator. So, and naturally carries with it the issue of uncertainty. This uncertainty is necessary because one needs to estimate an unknown physical transformation that described by unitary operator. Okay. So let us define. Okay, in this topic, we already have a paper last year. Okay. Then for this section, we try to understand the uncertainty ratio in terms of standard deviation. So what we should know about. So we must note that the uncertainty principle is one of the characteristic properties of quantum theory based on incompatibility. So therefore, the notion of incompatibility can be seen in this equation, which is, I think this equation was made by Robertson and Schrödinger. Okay, where D is the uncertainty for a pair of non-commuting observable. So this has motivated the study of uncertainty of pairs of unity operator, which reported by these two papers, and then which is Massa report in 2008 obeys the commutation relation, and Bachi, I think they formulated uncertainty relation for a pair of unitary operator and providing tighter bounds. So in this both paper, you can see that the uncertainty of an operator U here is defined in terms of variances, which is delta U here. Okay, and this can be understood as the uncertainty in the cat state, which is we have cat psi here, associated to U in the context of overlap the state cat U, cat psi here, sorry, cat psi, and the evolved state U acting on the cat psi. So extending this to a pair of unitary operators, U and V would reflect the distinguishability of two distinct unitary state of evolution. So this is how we interpret the distinguishability of a pair of unitary operator. However, it is not clear the terms of uncertainty of unitary operator that would imply in the context of distinguishability. So for example, an example given in sigma x and sigma z in two-dimensional quantum system, actually the uncertainty ratio given as this, but actually it's actually easy to distinguish these two operators actually. So in other words, the uncertainty ratio in terms of standard deviation does not give a clear term what kind of in the context of distinguishability, how well does one can distinguish two unitary state evolution, unitary operation from the original state here. Okay, but and then what is our purpose? Actually, we want to have a notion that will actually reflect the uncertainty one can have when testing such unitary operator. So in other words, if one can test perfectly such an operator, then the uncertainty is zero. If you can distinguish that operator, the uncertainty is zero. But instead of one operator, we would like to have a pair of unitary operator. It means two unitary operator. So when we perfectly distinguishing the operators, then the tester has zero uncertainty with respect to both operators. So note that this testing operator is well established in the context of PPOVM. So PPOVM actually process positive operator value measure. Okay, yeah, this is. So we would like to have this kind of notion, but when we don't want to use it in terms of standard deviation, the uncertainty ratio. So what we do, we go for the uncertainty principle in terms of entropy. So it is known that the entropy uncertainty relation for observable of finite dimensional Hilbert space was first proposed in Deutsch in 1983, and then following conjecture of Krauss in 1987 and later improved by Arfin. So this is the very well-known uncertainty relation as in equation 25, which is this is Shannon entropy. Okay. So and then from this, based on this Shannon entropy, we would like to have as uncertainty of unity operator that actually would simply reflect the distinguishability of the unity operator. So based on this, we derive actually our uncertainty relation for a pair of unity operators actually. So we have two bounds, which is trivial bound. When we meant by trivial bound, it means that given a pair of unity operator V and W, if the entropy gives the value of 0, so it means they are perfectly distinguishable. It can say that they are in the same basis, therefore they are orthogonal to each other. So how we do that? We do the overlap between, let's say, W and V dagger acting on the ket chi j, and then ket chi I, the overlap, and then it will result in is equal to 0 or 1. So it means that you can distinguish W and V perfectly. So what about it means that V and W saturate the trivial bound. So what about maximum bound? So we have a proposition saying that let V and W here be two distinct bases for some d-dimensional subspace for LHD, which is this is the space of operating on the d-dimensional space. And then V and W are mutually unbiased, given that the Hilbert-Schmidt inner product here is equal to cert D. So we say that Vn and Wn saturate the maximum bound. How we going to do that? So we have the overlap between Wm, Vn dagger, ket chi j, and ket chi I is equal to 1 over cert D. Okay. So we consider two pairs of operator. This is for SU2, so it means D is equal to 2. So we have identity with the Pauli operator sigma y, and identity with I minus I sigma y, this is complex number, over cert2. So the projective measurement in both cases are given by as this, with ket chi 1 and ket chi 2 is given as equation 28. So we can see the overlap between sigma y and ket chi I and ket chi j, and I minus I sigma y over cert 2 ket chi I and ket chi j for ij is equal to 1 and or 2 can be depicted from the graph as follows. So this is the first one with identity with sigma y, Pauli operator sigma y here. And you can see the overlap, the maximum overlap between these two actually achieves 1 at the edges as well as the center. So from this, you can see it decreases in value up to 0.5, okay, before taking turn to increase at the center. So these edges correspond actually to projectors that project onto the point sphere. Okay, and then I think the center correspond to the eigenvectors of I sigma y, which is this is trivial tester. We don't want that. We don't want actually this trivial tester at the peak here, the center here. So we can see that actually the increasing from 0.5 up to 1 at the center is actually contributed by this actually. Okay. So what does it mean? It means that based on the trivial bound, okay, when you do the overlap is equal to 1, okay, so it means that you can definitely distinguish between the identity and sigma y, okay, they are orthogonal to each other. So what about identity with I minus I sigma y over square root 2? So you can see that maximum overlap between these two actually achieve 0.5 here. 0.5 at the edges. Okay, and then the at the center, the P here, actually the eigenvectors of the operator, which is this is trivial tester. We don't want that. We only look at the edges, and then you can see that this is actually identical because because this maximum overlap is actually solely come from this. Okay, so that's why they look identical. So what does it mean? It means that this operator I and I minus I sigma y over Z2 is actually indistinguishable because it saturates the trivial bound such as this is true. Okay, this is without square. When you square D, it's become 1 over D. So 1 over D, in this case, 1 over 2. 1 over 2. Okay, 1 over T is 0.5. Yeah. Okay, it means this pair of unitary operators saturate the maximum bound. So summary and conclusion. So the definition of MUB in first section is more general. And then one can always construct a minimum number of 3 MUB and the maximum number is approached for a very large values of D. And then the next section based on the isomorphism between the monoids defined for underlying sets of HD and that for MS, the number of MUB can be constructed for MS is actually D. And then the last section is the operator are distinguishable if the pair of unitary operators saturating the integral bound. And then whereas the operator that derive from two distinct bases which saturating the maximum bound, that two operators are MUB to each other. So this is our role of MUB in the context of uncertainty relation for unitary operators. So this is the future project that we would like to have. Actually, at the moment, we are working on the first at the moment, we are looking for this, the construction of MUB for higher dimensional D squared dimensional space. Okay, we already have for D is equal to 3, but we are trying look for D is equal to 5. And then we're going to have D is equal to 7. And if 5 and 7 have common recipe, then we could generalize it. And hopefully it can result in some paper. Okay, and then after that, we would like to have a proof of uniqueness of MUB construction for MS. And then we try to look for the existence of mutually unbiased bases consist of non-unitary bases on non-prime number. Okay, we try to look at this. And then we would like to have MUB in generalized bidirectional quantum key distribution QKD. As you know, in quantum information theory, when we talk about quantum key distribution, is the application that in quantum information. We would like to have our MUB in some of generalized protocol in bidirectional quantum QKD. Okay, with that, thank you.
Okey, terima kasih Dr. Rinie. Seterusnya sekarang sesi soal jawab. Saya buka untuk para pensyarah bertanya soalan ataupun mohon pencerahan, dipersilakan. Kepada peserta yang mengikuti kolokvium ini melalui saluran YouTube boleh bertanya soalan melalui chatting. Yang bertugas akan membantu untuk menyampaikan soalan tersebut. Dipersilakan.
Ya, Dr. Amira.
Assalamualaikum warahmatullahi wabarakatuh. Okay, first of all, Dr. Rinie for very impressive presentation. So I have here, how is this your studies used in our everyday life? Because of I'm away from your background, so I don't have any idea why this study is needed actually. And the second thing, when you present it, you are concerned about finding the maximum number of the mutual unbiased base, right? Yeah. So what is the important to find the maximum number actually?
Okay, thank you for the question. Okay, actually, when we talk about quantum information theory, actually in Malaysia, we only have theoretical but not experiment. Okay, because to have experiment, the setup in Malaysia is costly, and I think the only one we have in is our university, International Islamic University, Malaysia, where I have my PhD there. And it's still, there is no student who wants to do it because we don't have any experts of this. The lab is there, but there is no expert. But when I went to a conference in Italy, they were advanced. They have already experimented for a very, I think, range for up to, if I'm not mistaken, for 400 meters of, I'm not sure, but the range is quite larger, whereas we have not started yet. So this is, even though I can say that if we would like to have a quantum information in our country, we need to do collaboration with other countries such as in the European, because we have no expertise in this. Okay, we have no expert in this. Well, yeah, theoretically yes, but not experimental. So it's because it's very costly. So we don't want to get behind too much. So I think this is a new frontier in our science and technology. So we should take part actually. Okay, for the second question is, okay, why is it important to have maximum? Because when we talk about maximum, it means you cannot go beyond that. Okay, we cannot go beyond that, because that's why it's very significant to have something you do that you have a maximum, so that it cannot go beyond that. For mutually unbiased basis, you can always have, for every dimension is d plus 1, regardless that d is d squared or subspace. You can also have d plus 1. That is maximum. No one can go beyond that. Okay, that's what we're trying to do. When you do something, you have to go at the maximum level that no one can go beyond that. That's a very important result actually. Okay, am I myself clear, Dr. Amira?
Yes, thank you so much for your explanation.
Okay.
Okey, soalan lain. Terima kasih Kak Amira atas soalan yang diberikan. Okey, ada sesiapa lagi nak bertanya soalan? Silakan. Dr. Narinie, soalan daripada YouTube tak ada, Dr. Narinie? Tak ada Okey, jika tiada apa-apa lagi isu untuk dibangkitkan ataupun soalan, tiada soalan lagi, kita tangguhkan kolokvium kali ini dengan surah Al-As dan tasbih kafarah. Sekian, wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih semua.
Okay, thank you.